We're now going to begin an in-depth study of applications of integration. So we're going to take a look at things like calculating volumes of solids, surface area for solids, arc length of curves, and then various physics topics like work and fluid pressure. Now to start, the first thing we're going to look at here in this lesson is area between curves. So we're going to start out with a statement of this result. If we let f of x and g of x be two continuous functions defined over an interval a, b, and let's also assume that f of x is larger than, greater than, or equal to g of x, then the area of the region A bounded between the two curves is given by this quantity. So it's the definite integral from a to b of f of x minus g of x. So down here we have a graphic of this. So if this is the function f, the upper curve, and the lower curve here is the function g of x, then we're saying that the area of the shaded region in between f and g, so this area right here, a, is equal to the definite integral of f of x minus g of x. Now this result is pretty easy to see graphically if we take a look at this. So if we want to evaluate this area A, and we want to verify that result that we just stated, the integral of f minus g, just take note of this. Down here we have a shaded region that's bounded between the x-axis and the graph of f of x. So the area of this shaded region would then be, by the fundamental theorem of calculus, the definite integral from a to b of f of x dx. Now over here, this curve, the lower curve, that's the function g of x, and so the area of this shaded region right here, bounded between the graph of g and the x-axis, well, that area right there is going to be the definite integral from a to b of g of x. So you see, if we take this shaded region and subtract from it this shaded region, which in this graph over here would be like this region right here, well, you can easily see that we get the gray shaded region up here. So we see that the area A up here is simply this shaded region minus this shaded region. Take that shaded region away. And of course, by properties of the definite integral, this is just equal to and we have our result that we stated previously. Now this isn't quite a complete proof of the result, however, although it is certainly true, because we didn't take into account what happens if this graph G, the way we drew it here, like what if it drops below the x-axis like this? You know, what if it did something like that? Then, you know, really, this doesn't really represent the area bounded between the graph of g and the x-axis anymore. If you remember, it would actually be the sum of the signed areas, although the result would still hold. So here's a more complete proof of this result, and the proof that we're going to look at now is actually a little more useful for what we're going to do soon with respect to volumes of solids of revolution. So we'll see that the proof that we do next will use this technique in upcoming sections. So let's take a look at a little more complete proof of this. Now before we look at the proof of that result, let's just recall one thing from the fundamental theorem of calculus. Recall that if we look at the limit of the summation of f of xi times delta x, that this quantity right here, in the limit as n goes to infinity, is equal to the area bounded between the graph of f and the x-axis for x between a and b, and by the first fundamental theorem of calculus is equal to your definite integral from a to b of f of x dx, which, recall, is the antiderivative of little f evaluated at b minus the antiderivative of little f evaluated at a. This is just a statement of the fundamental theorem of calculus. Now, when you're in order to understand this a little bit better, just to recall what was going on there, let me show you this graphic. So over here we have the graph of just the function f of x that we're referring to right here. Now you should take note that for each I, this quantity right here represents the area of each of these shaded rectangles. For example, in this graphic right here, the n is equal to 4, and so f of x1 times delta x, if we put the x1 right here, you see f of x1 would be this height right here. That distance right there is f of x1. And then when we multiply by delta x, which is the distance of the little subinterval, that's delta x. So this distance here is delta x. So f of x1 times delta x gives us the area of this first rectangle right here. So in general, when we look at f of xi times delta x, that's just going to be the area of the ith rectangle over here. And when we sum all of them up, that's what this means. You add up the area of all of those rectangles, you get a reasonably good approximation to the area underneath the graph of the function from a to b. So you see the area, when we add up the area of all these rectangles, we get a pretty good approximation to the area under the curve. However, it's not perfect, of course, because you see this rectangle goes above the curve right here, and here this one is a little bit below the curve, so it's not perfect. However, as we let n go to infinity, it becomes a near perfect approximation to the area under the curve. And in the limit, it is the exact area. So notice that in this graphic, if I let n get larger, you'll see how these gray rectangles perfectly fill in the area under the curve. So just watch that, what happens as n increases. You see, as n is increasing, we're getting a better and better approximation to the area under the curve if we add up the area of each of those rectangles. And you see, as n gets really big, it's near perfect. And in the limit as n goes to infinity, the summation is exactly equal to the area underneath the graph of the function and above the x-axis for x between a and b. So whenever you see something like this right here, you should think of this quantity right here as turning into this integral symbol right here, and the f of x, just change the xi into an x, so this is the function that you're integrating then, and the delta x becomes a dx. So now back to our proof of the area between curves. So right here, if we take the interval from a to b and partition it into n subintervals, the area, for example, of this ith rectangle right here, call it delta a sub I, that's going to be like that. Right? So if I pick xi to be any value in the ith subinterval, that would be the interval going from here to here. F of xi is going to be the distance from here to here. G of xi would be the distance from here to here. And if I subtract them, we would get this distance right here is going to be f of xi minus g of xi. So the height of this rectangle, this distance, is f of xi minus g of xi. And then when we multiply by delta x, which is the width right here, so this distance right here is delta x, we get the area of the rectangle. So if we add all of those up, so if we add up the area of all of these gray rectangles down here, we get a good approximation to the area between the graph of G and the graph of F. And then if we take the limit as n goes to infinity, we get the exact area bounded between G and F, and so this is the exact area, A. And we see now that this term right here turns into an integral. We replace all the xi's with just x's. The delta x becomes a dx, and then we go from A to B. The A and B are not explicitly stated up here in the limit of the sum, but they are there. And then we have our result. So now let's take a look at a few examples. Now for this example, we want to evaluate the area of the region bounded between these two curves, the curves y equals x and y equals x squared minus 2. So the first thing you want to do for these problems is graph your two functions, determine the interval over which you need to integrate, and also determine which function is the larger function. So down here we have the two functions graphed. Now this curve right here, that's the graph of the parabola, and then the graph of y equals x is this one, of course. And so it looks like x is the larger of the two functions. And so this is the region here that we want to find the area of, this red shaded region. So we need to determine the interval over which we're going to integrate. So we need to find where the two functions intersect. So if we set x squared minus 2 equal to x, and we can solve this for x. And this factors nicely. So we found that the x-coordinate of the intersection points here are -1 and 2. So right here is -1 on the x-axis, and right here is 2. And so to find the area of this region, we need to integrate from -1 to 2 of the upper curve minus the lower curve. And so the area then of this region is going to be And so there you go, we found the antiderivative of x minus x squared plus 2. Right here it is. And now we just need to evaluate this from -1 to 2. So that's going to equal And then this quantity just evaluates out to 9/2. And so that's our area of the region over here, 4.5. Let's take a look at another example now. Now for this example, we want to find the area bounded between the graphs of the sine function and the cosine function for x between 0 and pi. So the first thing you want to do is graph the functions that you're working with and try to determine the region that you're trying to find the area of. So here we have the graph of the cosine function right here, and the graph of the sine function right here. So the region we're trying to find the area of is the region here and here. So we want to find the total area of this region. Now the problem that we see here is that for this region right here, call this region R1, the cosine curve is above the sine curve. So for this region we would have to integrate cosine minus sine. However, over here, let's call this region 2, we see that the sine curve is above the cosine curve. So we would have to integrate sine minus cosine. So we see that we're actually going to have two integrals here. We're going to have to integrate. So it looks like for this problem, we're actually going to have to evaluate two separate integrals. An integral giving us the area of region 1, and then an integral giving us the area of region 2. So to find these two integrals, we have to find where these graphs intersect. You notice there's an intersection point right here. So that intersection point occurs when the sine equals cosine. Now, sine equals cosine from 0 to pi when x equals pi over 4. You can see this from the unit circle diagram. This is a very common result here. So the area of region 1 is given by Okay, so notice we took the integral of the upper curve minus the lower curve over the interval from 0 to pi over 4. Antiderivative of cosine is sine. Antiderivative of sine is negative cosine, so minus negative cosine is plus cosine. And then we have to evaluate that from 0 to pi over 4. So that's going to be the sine of pi over 4 plus cosine pi over 4. Minus sine of 0 plus cosine 0. Now these two terms are root 2 over 2. This term is 0, and this term is 1. And so what we're getting here is root 2 over 2 plus root 2 over 2, that's root 2, minus 1. And so there you go, that's the area of region 1. Now we have to find the area of region 2 and add them together. So the area of R2, that's going to be the integral from pi over 4, pi. Now we have to go sine minus cosine, you see, because they flipped. Now the sine is the larger curve, and the cosine is the lower curve. Sine is the upper, cosine is the lower now. Antiderivative of sine is negative cosine. Antiderivative of cosine is just positive sine. Plugging in pi and pi over 4 in here and subtracting, we get this. Now cosine of pi, we see from the graph here that is -1. So minus -1 is just going to be +1. Sine of pi is 0. You can see that from the graph of sine here. Sine of pi is 0. And cosine of pi over 4 and sine pi over 4 are both √2/2, as we saw up here. And so this term right here is going to be -√2. Right? That's by adding together √2/2 plus √2/2 gives you √2. And we've got negatives. And so we're ending up with here 1 plus √2. So therefore our total area of the region bounded between these two curves is the area of R1 plus the area of R2. That's the area of R1 plus this. That's the area of R2. And of course we get 2√2. And there we go. We have found the area, the total area of the region bounded between the sine and cosine curves. So the important thing to notice for this example is how we had to break the integral from 0 to pi into two separate integrals, because the upper and lower curves switched places at pi over 4, which is in between 0 and pi. And let's take a look at one more example here. So for this problem, we want to set up the integrals that could be evaluated to determine the area bounded between the graphs of this function and this function. So the first thing to do once again is to graph the equations to get an idea of the regions that you're trying to find. So down here we have the graph of this one right here is the parabola (-x² plus 2x). And this curve right here is the graph of the cubic. So we see that the curves trade places as we move from left to right. So it looks like we're going to have two separate integrals to find the total area of these shaded regions. So let's label this region here R1 and this region R2, and we want to find the area of each of these regions. So we need to find where these curves intersect, and that'll determine our limits of integration. So if we set them equal to each other, and then solving this equation, right, that's what we get. You notice how the x squares here, the negative x squares cancel, bring the 2x over, we get -12x, and then this can be factored. And this term can further be factored as and then we see that this has solutions. -2, that comes from setting this equal to 0. +2, that comes from setting this equal to 0. And setting 3x equal to 0, we get 0 for x. So we have these three solutions. And right here they are on the x-axis. So the x-coordinate of that intersection point corresponds to -2 on the x-axis. This intersection point, the x-coordinate corresponds to x equaling 0, and that intersection point, the x-coordinate corresponds to x equaling positive 2. So now we see on for the region R1, the upper curve is the cubic, the lower curve is the quadratic, and so the area of region R1, that's going to be the integral from -2 to 0 of the upper curve minus the lower curve. And then subtracting this, taking a negative of this quantity, is going to be positive x squared minus 2x. And you could simplify this a bit, of course. You see these right here canceling, you get a negative 12x. Now the area of region R2, now the upper curve is the quadratic and the lower curve is the cubic polynomial. Now notice we're going to integrate from 0 to 2 to find the area of this region. And now the upper curve is this one. And then we have to subtract all of these terms. And there you go. And also notice here, once again, the x squares do cancel again. And now for this one, we would get the integral of -3x cubed plus 12x. And you can evaluate both of these to find the area of each of these regions. The first one, I'll tell you what that evaluates out to, and you can verify the algebra on your own. So this integral works out to equal 12. And this one down here, actually this turns out to be the same thing, 12. And so your total area is 12 plus 12, or 24. So that's the total area. And once again, notice how we had to break this up into two separate integrals because the curves switched places partway through between -2 and 2.